beginning of learning target 6C, and in this video we're going to learn about indefinite integrals and U-substitution. So we are going to break this section into two different videos and spend 2 days talking about it in class. And in this video we're going to introduce what U-substitution is and apply it to some algebraic and trig integrals. So before we jump into U-substitution, let's review our two basic integrals that we learned in our last video. So the two basic integrals we have is that the integral of x to the n dx is equal to x to the n plus 1 all over n plus 1 plus c. And this works anytime that our exponent is not equal to -1. So any positive number works, a fraction works, I just cannot have that exponent equal to -1. And this is kind of like our power rule for integrals, where we're adding 1 to the exponent and then dividing by that new power. And we have the plus c here because we don't have bounds on this integral. The other basic integral that we learned in our last section was if I integrate a constant, that is equal to that constant k times x, and again plus c since I don't have any bounds. Down below in our first example, we kind of have two warm-up problems here. Why don't you guys pause the video right now and complete the integral in part A, and then we'll check it together. So in this first integral here, we have 2x to the 9th minus the 5th root of x minus 1 over x cubed plus pi dx. So I'm going to rewrite some of these so that I have them all as exponents. So I still have 2x to the 9th. For the 5th root of x, we can rewrite that as x to the 1/5 power minus the 1 over x to the 3rd, we're going to rewrite as x to the -3, and then we still have that plus pi dx. So I haven't integrated anything, I have not found an antiderivative yet. All I've done is rewritten the integrand so that I can see what all of those exponents are. From here, I can apply the power rule to integrals, so I end up with 2x to the 10th over 10 by adding 1 to that exponent of 9, minus, on the x to the 5th, when I add 1, we get x to the 6 over 5, since we get 1 plus 1/5, and to add those two together, we would need a common denominator, so we could rewrite the 1 as 5 over 5, and so that's how we end up with the 6 over 5, divided by that same exponent of 6 over 5, minus, we'll do the same thing with x to the -3rd. When I add 1, we get x to the -2nd, all over -2. And then for the pi, since pi is a constant term, the integral of any constant is that constant times our variable of integration, which is x for us. And since we have no bounds on our integral, we'd end up with that plus c. Just to simplify this down, we can reduce the 2 over 10 to be x to the 10th over 5. When I divide through by a fraction, it's the same as multiplying by the reciprocal. So we could rewrite this as 5 over 6 times x to the 6/5. And then for our negative exponent, we can go ahead and flip that down into the denominator and be x to the +2. And I can also multiply those two negatives to get a positive, and I still have that 1/2 plus our pi x plus c. And that would be our final antiderivative for example A. Let's do the same thing with example B. So here we have the integral from -1 to 4 of x to the 5th minus 8 dx. Why don't you guys pause the video here and do this one as a review and pay attention to the fact that we do have bounds this time. So for this integral, I'm still going to integrate it using our power rule and our constant rule. So x to the 5th, the antiderivative of that is x to the 6 over 6, minus the antiderivative of -8 would give us -8x. Now because I have bounds on the integral, I'm not going to write a plus c. Instead I have that evaluation bar, and then I have my bounds on the outside of that. So this is saying I still need to evaluate my antiderivative from -1 to 4. Now that we've found an antiderivative, I can apply the fundamental theorem of calculus by substituting in the top bound minus the lower bound. So we end up with 4 to the 6th power over 6 minus 8 times 4. That is that f of 4, so that top bound subbed in, minus our lower bound subbed in would be -1 to the 6th over 6 minus 8 times -1. And we want to make sure that we're being careful and we have parentheses around our second quantity here where we subbed in the -1, and we also do need parentheses around that -1 when we raise it to the 6th power. We could simplify it, but for the sake of time, I'm just going to leave that as our final answer. So I did want us to see some review just to refresh our memory, but also talk about the fact that each one of these integrals is very nice because it's a bunch of nice functions added and subtracted together. And as we start to look at more and more complicated integrals, we're going to need a way to approach them. Now, when we learned derivatives, we started with the power rule, and we started with taking the derivative of constants, just like we're doing here with integrals, and then we started learning about the product rule, quotient rule, and the chain rule. Well, there is no product rule, quotient rule, or chain rule for integrals. Instead, because integration is undoing differentiation, we have to figure out how to undo each one of those rules. So in integration, we have what we call techniques of integration. And for our course of AB Calculus, we're going to learn one technique of integration, which is called U-Substitution. And U-Substitution ultimately will undo the chain rule. As you guys go take other classes, you're going to learn other techniques of integration, such as integration by parts, which undoes the product rule. You might learn how to integrate partial fractions, integrate some other more complicated functions as you continue on with your math classes. And the reason that this happens is, well, what happens if I have an integral like this, where I have the integral of 7x minus 3 squared dx? Well, one option I could do is I could just FOIL that out. I could multiply 7x minus 3 times 7x minus 3, multiply everything out, and just get left with 3 different terms, which I can then each integrate individually. That's not too bad to do. But what if I had the integral of 7x minus 3 to the 50th power? Well, I could multiply all of that out. Personally, I'm lazy and I don't want to have to multiply all of that out every single time. That seems a little unnecessary. There should be some other way to do that. So what we're going to learn is a technique of integration that allows us to integrate problems that look like this. So this technique of integration is called U-Substitution, and what it is ultimately undoing is we are going to undo the chain rule here. So what we have on the screen is we have the integral of f of g of x times g prime of x dx. And hopefully this integrand here looks familiar. That was what we got when we applied the chain rule. Well, if we were to undo the chain rule, we should just get left with our antiderivative, capital F, of that original input of g of x, and then plus c since we don't have any bounds. So again, that capital F is our antiderivative of our lowercase f, and what we're going to do through the U-Substitution process is undo the chain rule. So we're going to ultimately let u be equal to g of x. So we're going to make that choice. And I'm going to choose u to be g of x since it's the inside function. Then from there, when I take the derivative of that, I would end up with du equals g prime of x times dx. I do have a typo in your course reader. I forgot to type out the dx in there, so make sure you add it. And I want to talk about why that's true. So on the side over here, I've got the integral of f of g of x times g prime of x. Now we're making this choice here that I'm putting the star next to choose u to be equal to g of x. That's where the name U-Substitution comes from, because we're going to replace, well, not really replace, but we're going to substitute in so that instead of being in terms of x, we're going to actually end up in terms of u in our integral. So we're going to let u equal g of x. Well, we can take the derivative of this. The derivative of u with respect to x is du over dx, derivative of u with respect to x, or we could use the notation u prime, and that would be equal to the derivative of g of x, which is g prime of x times 1. Then from there, what I'm doing is I'm moving that operator of that dx, or that differential, to the other side, and I end up with du equals g prime of x dx. And now from here, I'm replacing everything. So if u was equal to g of x, instead of having f of g of x, I'm going to end up with f of u, and instead of having this g prime, well, I shouldn't, green, there we go. Instead of having this g prime of x dx in there, since g prime of x dx equals our du, I can replace that. So we're making a replacement on both parts of the integral so that anywhere that we had an x, which was our original variable of integration, we're going to replacing it so that we are all in terms of u. And down here in your course reader typed out is that whole process that I have on the side. And once we integrate from there, we can actually get the antiderivative, and we would have f of u then, where we have capital F of x since it's the antiderivative, plus c, and our last step would be to sub back what u is equal to, which is g of x. So we're going to go through quite a few examples in this video where we learn about the setup, how to replace the integral all in terms of u, and then we will continue to integrate from here, and we'll get our antiderivative of f of u plus c. And then from there, our last step will be to replace what u is equal to, which is that g of x. So we'll end up with our antiderivative of g of x plus c as our final answer. So our goal first is to replace all the x's in terms of u. Then we will integrate. After we integrate, we will substitute back any values for u so that we're back in terms of x, which was our original variable. Couple things to keep in mind when choosing u. The first thing is that we want to make sure that u is the inside function. So when we applied the chain rule, it happened because we had a composition of functions. We had an inside function, g of x, and an outside function, f. So we want to make sure that that u is that inside function. I also have to make sure that the derivative of u is somewhere in the integrand as well, so that it can be replaced when we take that derivative step. And we'll see this through quite a few examples. So let's look at our first example here. We want to make sure we're going to integrate all of the following, and I'm also going to require that we state our u sub and our du. So that is going to be part of the work that's going to be graded on any learning check or your final in this class. So in our first example here, we have the integral of 1 minus x all to the 9th power dx. Well, I've got to think about what functions I have. I have 1 minus x, and then I have this 9th exponent. So what do you guys think? Which one is the inside function and which one is the outside function? So in this case, 1 minus x is our inside function. So that's what we're going to let u be equal to. So I'm going to let u be equal to 1 minus x. Well, from here we can take the derivative of u with respect to x. Our derivative of 1 would just be 0. Derivative of negative x would give me negative 1 then. Now we can start doing this replacement. So in our original integral here, I'm still going to have an integral sign, but instead of 1 minus x to the 9th, we're going to end up with this u to the 9th power. And now we need to figure out how to replace our dx, because that's all the extra stuff that's left over. Well, my dx comes up in our derivative here, and if I were to isolate dx, then I could figure out what to replace it with. So I can multiply both sides by dx here, and I get du equals negative 1 dx. And then our last step would be to divide through by that negative and get negative du equals dx. What that's going to allow me to do then is replace this dx with the negative du. So when I replace that in, it is being multiplied to the u to the 9th. And I've now replaced everything from my original integral in terms of x. Now before I integrate, this looks a little funky here. I'm going to take out any scalars that I have. So we learned from properties of integrals that any scalars can be taken outside of the integral, and that negative 1, which is being multiplied, is a scalar there. So I'm going to take that out of the integral, and we'll have negative the integral of u to the 9th du. Now our u sub is complete, and we can go ahead and actually find an antiderivative from here. Using our power rule for antiderivatives, we know that the integral of u to the 9th would be u to the 10th over 10, since I'm adding 1 to the exponent and dividing by that new power. Because I don't have any bounds, I have to make sure I have that plus c. Now that we've integrated, I can go ahead and substitute back my u. So I end up with negative 1 over 10. Instead of u to the 9th, I'm going to get 1 minus x. Or instead of u to the 10th, I'm sorry, we'll get 1 minus x to the 10th, and then plus c. And that will be our final answer here. One thing I forgot to say earlier is that when you do a u-substitution, your integral that you end up with before you integrate, once it's all in terms of u, should be a much simpler integral. In fact, it should be one of our basic integrals that we've learned. And so since the only two basic integrals that we've learned is the x to the n, or a power rule integral, as well as a constant, is for all of these first couple that we're doing, we should be able to rewrite it as just u to a power once we've done the u-substitution correctly. Let's look at our next example here. So in this next example, we have the integral of 4x minus 3 to the 5th dx. Why don't you guys pause the video right here and decide what your u would be equal to. So for here, we want our u to be our inside function. The 4x minus 3 is our inside function, and that 5th power is our outside function. So u is going to be 4x minus 3. I need to figure out what my du is. I'm going to go ahead and just always multiply that dx to the other side just to save me a little bit of time. So our derivative here of 4x minus 3 would be 4, and then the dx, since we'll bring that over to the other side. From here, let's start to replace what we have. So instead of the 4x minus 3, we're going to end up with u to the 5th, since we're replacing 4x minus 3 with u, since that's what it's equal to. And the last thing I have to replace is we have to replace that dx. So in this du equals 4 times dx line, we want to isolate that dx to be able to replace it. What could I do to get dx by itself? We could divide through by 4, and we would end up with 1/4 du equals dx. And from here, then, we can replace that dx with that 1/4 times that du. Just like we did before, any scalars we want to take outside of the integral, so we get 1/4 the integral of u to the 5th du. Now that we've done our u sub, we can actually integrate. So in these problems now, we're not really doing any we're not integrating it until after we've replaced everything in terms of u, and that involves both the integrand as well as that variable of integration. I could not leave a dx here and just have u to the 5th times dx, because it's not possible to integrate if my variable of integration is different. Why don't you guys pause the video here and find the antiderivative for u to the 5th. So the antiderivative of u to the 5th is going to be u to the 6 over 6 using that power rule. Because we don't have any bounds, we're going to get that plus c. That kind of looked like a 4. Let's fix that. So that was a u, there we go, to the 6. And now from here, a couple things I can do. I definitely need to replace what u is equal to, so I'll have to substitute back that 4x minus 3. And I'm also going to go ahead and multiply any scalars just so that I can rewrite that as one term. So the 1/4 times the 1/6 would give us 1 over 24. Replacing the u, we get 4x minus 3 all to the 6th power plus c then. And that would be our final answer. In this section, we're just going to focus on indefinite integrals with U-substitution, so none of these problems are going to have bounds yet. In our next learning target, we'll build in what happens with the bounds when we go through to solve. So look at example C. Here we have x times x squared plus e to the 4th all to the 100th power dx. So in this one, we have a little bit more going on. We've got an x outside, we've got an x squared plus e to the 4th. All of that is being raised to this 100th power. Why don't you guys pause the video here and think about what our u would be? What would our inside function be? So just like before, our inside function is going to be what's being raised to the power. So x squared plus e to the 4th will be our u. And let's start setting this up right away. So the first thing I notice that I can replace is instead of x squared plus e to the 4th, I would end up with a u to the 100th power. Unlike the first two examples, though, I have something else to replace. I don't just have to replace the dx, I also have to replace that x there. Well, let's take a derivative and see if we can figure this out. So when we take the derivative of x squared, we end up with that 2x, and then the derivative of e to the 4th is actually going to give us 0 since e is a constant, and then we have that dx that we're always bringing over to that other side in that same step. Well, from here, now that I have what my du is equal to, I can start to think about, well, how can I replace the x and the dx? And these are not two separate quantities, they're actually being multiplied together because it's technically x times this quantity to the 100th and then that dx. So here, my goal is to solve for not just dx, but x times dx so that I can figure out what that is equal to together. What could I do to get x dx by itself? Well, to get x dx by itself, I'm going to divide through by 2, and we get 1/2 du equals x dx. And from here then we can replace that x dx with that 1/2 du. Just like we did in the last example, that scalar of 1/2, I'm going to go ahead and take outside of the integral, and we get 1/2 times the integral of u to the 100th du. Now our u substitution is complete because we've reset up this integral all in terms of u. Why don't you guys pause the video here and find your antiderivative, and then substitute back what u is equal to and get your final answer in terms of x. So for our antiderivative, we can apply the power rule. The antiderivative of u to the 100th is going to be u to the 101st power over 101 plus c, since we don't have any bounds. Then our last step here, I can multiply those and get 1 over 202. Substituting back the u, we get x squared plus e to the 4th to the 101st power plus c as our final answer. Now before we go look at the next example, I want us to think about why we had to worry about this extra x in problem C. So in problem A and B, what do you notice that's different with A and B? A and B are similar, but what do you notice about A and B versus example C here? So one thing I notice is what my u is. So although each one has a different u, in examples A and B, my u is a linear function. Both of these are just x to the first power. And the reason that that's helpful is that when I take the derivative of anything that's linear, I just end up with a constant term. Notice in both of these du's, I have no more x's. I just have a number times dx. Versus in example C here, our u is a quadratic function. I have an x squared. So when I take the derivative of that, I end up with a linear function of this 2x. Although when we first looked at this problem, it looked challenging because I have something extra outside. But in fact, if that wasn't there outside, I could not actually do u substitution. We need that x outside because that's part of this g prime. So if I scroll back up to where we had it in general, when we have an inside function that's quadratic with that x squared, we need to have an extra x out here to balance out that being in the derivative because that's part of that g prime of x. So although it looked more complicated to start with, it's actually the same type of question. That's just part of our du that will end up being replaced. Okay, let's look at example D. So here we have the integral of 7x over x squared plus 1 whole quantity squared. Well, this definitely looks different now. We've got a fraction, but we know from algebra that I could rewrite anything as a fraction with a negative exponent. So I'm going to go ahead right away and just rewrite this as 7x times x squared plus 1 to the negative second power dx. And this is similar to the first example that we saw today. If we go back up to that very first example, when we had this 1 over x cubed, one of the first things we did was we rewrote it as x to the negative third. Same concept down below here, although it is definitely a much more complicated integrand here. Anytime I have that fraction in there with a polynomial, I can go ahead and rewrite that as a negative exponent up above. Now that we've done this, why don't you guys pause the video and decide what your u would be. What do you think your u is going to end up being? So in this case, our u is going to be that x squared plus 1. That's the inside function here. If we take our derivative of that, we'll end up with 2x dx. Now let's look back at our original problem. So the 7, we haven't seen a scalar in the problem to begin with, but we know from properties of integrals that that scalar can come outside. So I can in fact leave that in my setup in terms of u. I'm just going to take the 7 out to begin with. Now the x we'll come back to, but that x squared plus 1, that becomes our u to the negative second. And what I'm left to replace, again, is this x times this dx. Well, we have that in our du equation. To get that by itself, I can again divide through by 2 and get 1/2 du equals x dx. From here then, we can replace that to get that 1/2 du instead of the x dx. And just like we've been doing, I'm going to take out that 1/2 as a scalar, so we end up with actually 7/2, the integral of u to the negative 2 du. Now we've reset up our entire integral in terms of u, and we've completed our u substitution. From here, we're going to integrate in terms of u, and then replace back so that our final answer is in terms of x. So why don't you guys pause the video here, find your antiderivative of u to the negative second, and then finish off the problem. So to check this, our antiderivative of u to the negative second would be u to the negative first, since we're adding 1 to that exponent, over negative 1, and then plus c since we don't have any bounds. From here, I can rewrite that as negative 7 over 2 times 1 over u, since that negative exponent can be flipped back down. And from here, replace our u, so we get negative 7 over 2 times 1 over x squared plus 1, and then plus c. And that would be our final answer then. Let's look at another example. So for problem E here, we have the integral of 4x squared times 5 minus 3x cubed all to the 5th power dx. Why don't you guys pause the video and decide on what your u would be. So for this example, our u is going to be the stuff that's being raised to the 5th power. So that would be 5 minus 3x cubed. The derivative of that would then be negative 9x squared dx. Now that we decided on our u and found our du, why don't you guys pause the video and rewrite this integral all in terms of u. But hold off to integrate, let's just check that step together. So we want to get to the step where we have an integral all in terms of u. So to check that, just like before, I can take the 4 outside of the integral. So I get 4 times the integral. Instead of all of this to the 5th power, it will become u to the 5th power. The last thing I have to replace is that x squared dx. So I can divide through by the negative 9 and get negative 1 over 9 du equals x squared dx. So that gets replaced in there. And then from here, I can take that scalar out as well and get negative 4 over 9, the integral of u to the 5th du. Now my integral is all in terms of u, so I can go ahead and find an antiderivative and then substitute back in, so our final answer is in terms of x. Why don't you guys pause the video here and complete example E. So to check this together, the first thing I'm going to do is get my antiderivative. So the antiderivative of u to the 5th will be u to the 6th power over 6 plus c. Then from here, substitute back my u, and I can go ahead and multiply in my coefficients, and I get negative 4 over 54. I would get 5 minus 3x cubed, all to the 6th power, since that's what our u is equal to, plus c. And we could, now that I'm realizing, actually reduce that coefficient in front, so we could reduce that down if you guys would like to. Okay, so we've seen quite a variety of examples. I want to point out that in E here, the reason we had that x squared out front is because inside we had a cubic, and we know that the derivative of a cubic is quadratic, and so although that x squared looks complicated, it's actually necessary in order for us to do the u substitution. Let's look at example F. So here we have the integral of negative x to the 3rd times the square root of 2x to the 4th minus 1 dx. Well, this one looks a little bit different because we have a square root. But we've known from our basic integrals that anytime I have that square root, I'm going to rewrite it as an exponent. So instead of the square root, we'll get 2x times x to the 4th minus 1 to the 1/2 power. And then we'll also have that dx. From here, why don't you guys pause the video and decide on what our u will be equal to, and then find your du, and we'll check that together. So for this example, our u is going to be 2x to the 4th minus 1. So our du would be 8x cubed dx then. Now that we have our u, why don't you guys pause the video and reset up this integral all in terms of u, and then we'll check that together before we integrate. So to reset this up in terms of u, I can take out that scalar, which is that -1, and I get the integral of u to the 1/2. The other thing I need to replace is that x cubed and that dx, but we can replace that with a 1/8 du if I divide through by the 8 in that equation. So I get multiplied by that 1/8 du. If I take out all the scalars, we get -1/8 integral of u to the 1/2 du then. Now that our integral is set up all in terms of u, we can go ahead and take an antiderivative. So why don't you guys pause the video here and integrate this function and then substitute back in x, and we'll check our final answer together. So our antiderivative here of u to the 1/2 would be u to the 3/2 all over 3/2 plus that constant term. We can go ahead and substitute the u back, and I'm also going to start combining coefficients. So I have the -1/8. When I divide by a fraction, that's the same as multiplying by the reciprocal. So I'm multiplying by 2/3. Our u is going to be replaced with what it is equal to. We could leave our answer like that on a free response, or if we would like to combine like terms and reduce down that scalar, we would end up with -1/12, since 2/8 is equal to 1/4, and then a fourth times a third is a 12, and then all the rest of this would stay the same. And either of those last two lines would actually work as our final answer. So we've seen a variety of examples using some algebraic functions and the power rule for integrals doing U-substitution. We do have 4 more in your guys' course reader that I'm going to scroll down to now. What I want you guys to do right now during this video, let's see all 4, is I want you guys to decide on what you think your u is. I'm going to have us check that together in the video, and then we'll actually solve them together in class next time. So why don't you guys pause the video right here and decide on what your u is for each one of these problems, and then find that du. Okay, so let's check these. So for our first one here, example G, our u is going to be 2x to the 4th minus 8. So our du is going to be 8x cubed then, dx. For our example H, I would rewrite that fraction so that I have that negative exponent instead, similar to what we did in example D. And from there we can see that our u is -4x cubed plus 10, and our du would be -12x squared dx. Then for example I would again rewrite that square root as the 1/2 power, and we can see that our u will end up being 5x squared plus 34, which gives us a du value of 10x dx. And then for our last example on this page, we have a u this time is a little bit trickier to decide on because we have an 8x minus 1, so one quantity times this 4x squared minus 7 plus 4, all to the 7th power. And in this case, our u is actually the 4x squared minus x plus 4. And the reason I chose that over the 8x minus 1 is 2 reasons. One, it's a higher power, so when I take a derivative, I'm going to get that 8x minus 1 that way. The other reason is that's what's inside that 7th power, and ultimately the 7th power is my outside function, and we want u to be what's inside that. From here, we can see that our derivative then would be that 8x minus 1 times that dx. So tonight after the video, why don't you guys set up all of these integrals in terms of u, then find your antiderivatives, and we'll check those all together at the start of class tomorrow. Okay, now the next part of this video is we're going to bring back some trig functions. So at the top of this page, we have 6 more basic integrals, and all of these integrals are based off of the derivatives that we learned last semester. So for our first one here, the integral of cosine is equal to sine, and that's because last semester we learned that the derivative of sine is equal to cosine. So we're basically starting with all the derivative answers that we got, we're integrating those and ending up with the original functions that we took the derivatives of last semester. So we'll notice that we should know the integrals of cosine and sine. So the integral of sine is actually negative cosine because the derivative of cosine was negative sine. And then in our next one, you would think the next one should be the integral of tangent. But the integral of tangent is actually not a basic integral. It's something that uses a different technique of integration to be able to solve. And instead, the basic integral is actually the integral of secant squared. And the reason that is because the derivative of tangent is equal to secant squared. The other three basic integrals are also up here. The integral of secant times tangent of x dx is equal to secant of x plus c. Integral of cosecant of x times cotangent of x is equal to negative cosecant of x. And then the last one is the integral of cosecant squared of x is equal to negative cotangent of x plus c. And each one of these, again, is coming from our derivatives that we learned of all 6 trig functions last semester. So let's start applying some of these. And we are going to build up to some U-substitutions with these, but we're going to first just practice with these 6 basic integrals. And over time through practice, these do become kind of more recognizable for you guys as we continue to practice, but it might be something to do some flashcards with to make sure that we have all 6 of these memorized. So let's look at example 3a. We have the integral of 6 times sine of x dx. Well, I'm going to apply properties of integrals first, so I can take out that coefficient, so I get 6 times the integral of sine of x dx. And from here, if it's a basic integral, we want to just apply what the antiderivative is, and if it's not a basic integral, then we'll think about how we can use U-substitution to turn it into a basic integral. Well, in this case, the integral of sine is a basic integral. It's that second one that's listed up here. And we know that the integral of sine is equal to negative cosine plus c. So our final answer then, if I multiply the 2 coefficients, would be negative 6 times cosine of x plus c. Okay. Let's look at our next example. We have the integral of negative 5 times secant squared of x dx. Why don't you guys pause the video here and rewrite this and then decide if this is a basic integral or if this will require a U-sub. So in this case, I can rewrite it by taking out that scalar of negative 5, and we get the integral of secant squared of x dx. And from here, that is a basic integral. The reason I know that is because the derivative of tangent is equal to secant squared. So the antiderivative of secant squared would be equal to tangent of x, and then plus c since I don't have any bounds. And that right there will be our final answer for problem B. All right, let's look at part C. So in C, we have the integral of 7 over secant of x dx. Well, this looks a little bit more cumbersome because I have that fraction. Well, let's take the first step and let's take out the 7 because the scalar is not going to make a difference. We get 1 over secant of x dx. Well, when I look at my list of basic integrals, 1 over secant of x is definitely not up there as it stands right now. I can't do a U-substitution on this because if I were to U-sub, my U would be secant of x, but the derivative of secant of x is secant times tangent, and I don't have that in my problem either. So instead, I want to think about how I could rewrite this. And we're going to notice with some trig functions, it might take us to use some trig identities to be able to rewrite them to turn them into basic integrals. So how could I rewrite 1 over secant of x? Think about how it could maybe be rewritten in sine and cosine, since those are our 2 basic trig functions. Well, secant is actually 1 over cosine, so 1 over secant is equal to cosine. So we end up with the integral of cosine of x dx. That is a basic integral. Integral of cosine is equal to positive sine. So we end up with 7 times sine of x plus c then. That will be our final answer for that integral. So in these first 3, we didn't do any U-subs. We were either given a basic integral or we were given an integral that we could rewrite using trig identities as a basic integral. But now we're going to start to see what happens when we have to do a U-sub. And for trig functions, how that's going to change is the first way that it could change is maybe I don't have just an x in these spots. Maybe instead we get something a little bit more complicated that's our input to our trig function. So let's look at example D. Here we have the integral of cosine of 2x dx. Well, this looks really similar to a basic integral because it's just cosine of something. And this is one where we could use U-substitution to make it into a basic integral. So in this case here, our u is going to be 2x. So our du would then be 2 times dx, since the derivative of 2x is 2. I can then rewrite this integral. I'll still have the cosine. That's not getting replaced. The trig function is still there. That's ultimately our outside function. But instead of cosine of 2x, we'll get cosine of u. And now I need to figure out, well, what can I replace the dx with? Well, to get the dx by itself, I could divide through by 2, and we get 1/2 du equals dx. So I can replace that in there. I'm going to actually jump that together in one step and just take out the scalar of 1/2, since we saw a lot of steps before where we ended up always taking out that scalar. From here now, that's a basic integral. Looks pretty similar to what we ended up with in example C. And we know that the integral of cosine is equal to sine. But since it was cosine of u, then the integral will be sine of u. Still get the plus c. And then our last step is to replace that u in terms of x. So we get 1/2 times sine of 2x plus that constant term. And that will be our final answer. To example E. So in example E here, we have the integral of 6 times sine of the square root of x all over the square root of x dx. Well, this definitely got messier. Well, let's do what we can do right at the start. Let's take out that coefficient. I think it's helpful to do that so that we have less to look at inside of our integrand, and it's less to really keep track of. So left over inside of our integrand, we have the sine of the square root of x over the square root of x. Well, we need to figure out if this is a basic integral or if we're going to have to do a U-substitution. As it stands right now, this is definitely not a basic integral, so we will do some type of U-substitution. What do you guys think the u will end up being? So in this case, the u is going to be the square root of x, but I want to be very specific about which square root I'm talking about. It's only the square root that's inside the trig function. And the reason it's only the one inside the trig function is because the one in the denominator is actually part of our derivative. So if we take the derivative of the square root of x, well, I could rewrite that as x to the 1/2. So when I power rule that, the 1/2 comes down, and we end up with x to the negative 1/2. Well, the negative exponent we know is the same thing as that square root of x in our denominator, and I don't want to forget about the 1/2 in front either. So we get du is equal to 1/2 times 1 over the square root of x dx. And so when we go to do the u sub now, instead of having that square root of x, we'll end up with the sine of u. And what we're left to replace this time is this 1 over x times the dx. And I want to be very clear that this square root of x, because it's in the denominator, is technically a 1 over that square root of x. So when we're looking over here in our derivative equation, it's this whole 1 over the square root of x dx that I'm trying to solve for. And to solve for that guy, I would multiply both sides through by 2 to get rid of that fraction in front. So we get 2 times du equals 1 over x dx, and that allows us to replace the 1 over the square root of x dx with a 2 times the du. So although this looked very cumbersome to start with, and it's very kind of challenging because you're like, wait, I have a square root of x and a square root of x in two places. Shouldn't I make both of them the u? We have to remember that we also have to replace our dx, and sometimes that involves other parts of the integrand that we had to start with. So we kind of just want to take it one step at a time as we're replacing, and if we have to replace in more than one spot, we can go ahead and always add that in later. Now that we've replaced the entire integral in terms of u, we can go ahead and take out any scalar, so I'll end up with actually 12 times the integral of sine of u du. That is a basic integral now. Looks much nicer than what we had to start with. We know that the integral of sine is equal to negative cosine, So I get negative 12 then cosine of u plus c. And again, we're just going to have to make sure we've got those basic integrals memorized. Last step will be to sub back the u. We get negative 12 cosine of the square root of x plus c. And one thing to remind you guys of is you guys can always check your work. Remember, derivatives and integrals are undoing each other. So to check my work here, I should be able to take the derivative of this function and end up with the integrand that I started with. And if you take the derivative of our answer here, you will end up with the integrand that we started with. Okay, let's look at example F. So here we have two trig functions. We have the integral of sine of x over cosine cubed of x dx. Well, when we've got more than one trig function, unless it's one of the basic integrals up above, so where we have like secant times tangent or cosecant times cotangent, what's going to happen in these integrals is that one of those is probably going to end up being what u is equal to. And the way we can figure out which one would be our u sub is we want to pay attention to what are the other factors going into this integral. So in this integral, I also have a cosine cubed. And although it's written as cosine cubed of x, remember this is the same thing as sine of x over cosine of x, the entire thing cubed. And when we rewrite it out like this, it's a little bit easier to see the fact that cosine of x is actually my inside function here because it's being raised to another power outside. And one more thing I can do for this one is I'm going to actually rewrite it so that I have everything in one line, so that I'll have cosine of x to the negative third power instead. And I think it's easier to not have to deal with the fraction if I can avoid it. And in this case, I can definitely see now that my inside function is that cosine of x there, and so that's what we're going to make u be equal to. So in this problem, u is going to be equal to cosine of x. And the reason the sine is actually part of the problem is because the derivative of cosine is equal to negative sine of x dx. And so that sine of x is there because it's part of the du. If the sine of x wasn't there, this problem would be much more challenging and a u substitution might not actually work out. And again, I said at the beginning of the video, but there's many different techniques of integration, and in this course we are only going to look at integrals that are basic integrals or integrals that can be solved by u substitution. As you take other courses, there are other techniques that you will learn, and that's really where it becomes a juggling act of figuring out which method I need to use. And so the reason u sub is the first method that we learn in integral calculus is because that's really the first method I should try, because if it works out, it's the easiest method to solve an integral that we have. So let's go ahead and reset up this integral in terms of u. So we can replace the cosine of x, that will be u to the negative third. What's left over to replace still is the sine of x times the dx. Well, that's part of my du. And to get it by itself, the one thing I have to do is divide through by a negative sign to get negative du equals, sine of x. The negative sign went away. So sine of x dx. And now I can replace that with that negative du. Again, that negative we know is a scalar, so we can take that out. And we get negative times the integral of u to the negative third du. That integral looks much better than the integral that we started with. And one key thing with u substitution is that if you set up the u substitution correctly, the integral is going to look much nicer because it will be a basic integral now. Now we can apply the power rule actually. So we'll add 1 to that exponent and get u to the negative second over negative 2 plus c. Our last step here to do would be to sub back what u is equal to. I'm also going to multiply the negative 1 and the negative 2 to get a positive 1/2, as well as flip down the u to be u to the positive 2 and replace it at the same time. So we end up with a cosine of x squared in the denominator of that fraction. And that would end up being our final answer there. So there are some integrals that although they involve trig functions, they actually end up being a power rule because some trig function was raised to another power inside of there. Okay, let's look at part G here. So in part G, we have the integral of -4 times secant of 2x times tangent of 2x dx. Well, the first thing I notice is that -4. I'm going to take that out of the integral because it's not going to affect my U-substitution and it's not going to affect my basic antiderivatives here. Now we're left with the integral of secant of 2x times tangent of 2x. Well, this is actually really close to a basic integral. Although I have two trig functions here, the antiderivative of secant times tangent is equal to secant. And that was in, if I scroll back up, that was that first basic integral here in the right-hand column that we're going to be applying. What I noticed about this basic integral here is that both inputs have the same. They're both an x and an x, and I would like it to just be that single x so that I can make it a basic integral. Well, if we scroll back down to the problem we have, well, we have the same input. We have 2x and we have 2x. That's what ends up going to be in our U-substitution in this problem. And they both have to be the same thing in order for this U-sub to work. So in this case, our U is going to be equal to 2x. So our du is going to be 2 times dx. So I can start replacing these pieces, and I get the integral of secant of u times tangent of u. And so in this case, unlike in example 6, I'm actually replacing both of the two x's with the u, and that has to do with the fact that secant times tangent is my basic integral, so I need both of those there. The last piece to replace is that dx. And so if I divide through by 2, I could get dx by itself, so we get a 1/2 du then. So in the process, we pick up another scalar, which we can then multiply those two to just get a -2 out front. Integral of secant of u times tangent of u du. From here, now that my integral is all in terms of u, I can find my antiderivative. Antiderivative of secant times tangent is equal to secant of u plus our constant. Last thing to do is replace what u is equal to, and we get -2 times secant of 2x plus c. And that will be our final answer for this one. Look at a couple more examples together. So in example h here, we have the integral of 4 times cosine of x times sine to the 6th power of x dx. Well, a couple things right off the bat. I'm going to definitely take out the scalar, so the 4 is going to come out, and I'm also going to rewrite the sine to the 6th power as sine of x all raised to that 6th power dx. Now that we have it like this, why don't you guys pause the video and think about what your u sub would be. What do you think u will be equal to? So in this case, our u sub is going to be sine of x, because that's the inside function that's being raised to the 6th power. So example h and example f are actually really similar here. Although there was a fraction up above in example f, they're both ultimately going to turn into power rules. So I have a trig function raised to a power. The reason the cosine's there is that's part of my derivative. Derivative of sine is equal to cosine of x dx. And what this will allow us to do now is when we go to replace this, instead of the sine to the 6th, we'll get u to the 6th power. And then to replace the cosine of x times the dx, well, that's equal to du, so I'm replacing that with the du then. Now, this is a basic integral where we can apply the power rule. So when we find the antiderivative of u to the 6th, we'll end up getting u to the 7th over 7 plus that constant term, and then the last thing we need to do is replace the u with sine, since that's what u is equal to, and we end up with 4 over 7 times sine to the 7th power plus c. And again, if we take the derivative of that, we will get back our original integrand that we had to start with. Let's look at another example here. So in this integral, we have the integral of 6 times the quantity 1 plus tangent of x, all to the 5th power, times secant squared of x dx. Now I know this looks more cumbersome, but the only way we get better at problems is by trying them on our own. So why don't you guys pause the video right here and think about what your u would be equal to. And if you're not really sure, sometimes it's helpful to think about what u would be, then find its derivative and see if it works out, see if the pieces all line up there. So why don't you guys pause the video and decide on what u would be equal to. So in this case, there's two things that I think about that could be u. I have this 1 plus tangent that's all raised to the 5th power, and then I also have a secant that's technically raised to the 2nd power. So it looks like both are inside functions. Now if I remember from my derivatives, whatever I make my u, the derivative has to be there as well. So if u is 1 plus tangent of x, well the derivative of 1 is 0, so that's going away. Derivative of tangent is secant squared of x dx. And so I want to make my u be equal to 1 plus tangent because the secant squared is actually there just so that it's taken care of with that du. So in this case, I'm going to take out the scalar. Instead of 1 plus tangent to the 5th, we'll get u to the 5th. And then to replace that secant squared of x dx, well, that's exactly what du is equal to. And now I have an integral that's all in terms of u, so I've done my u sub correctly, and it is a basic integral, and it looks much nicer than the one we started with. Why don't you guys finish off this example by finding the antiderivative, and then substituting back what u is equal to, and get your final answer. So here, our antiderivative of u to the 5th will be u to the 6 over 6 plus c. Conveniently, those actually end up canceling this time, and we'll replace our u, so we get 1 plus tangent of x all to the 6th power plus that constant term. And that will end up being our final answer then. Now, there's another page of examples in your course reader. Just like we did before in this video, I want you guys to pause the video right now and decide on what u would be equal to for all of these, and then we'll just check that step together. So for our first one here, it is very cumbersome. We've got -7 sine of x times secant squared of cosine of x dx. Well, we've seen where we have sines and cosines before. We know that the derivative of each of these is the other function. So in this case, more than likely my u needs to be one of those two, since the derivative would be the other. In this case, since cosine is inside the secant squared, I'm going to make my u be equal to cosine of x, and that way my du will get rid of that sine of x that's outside that function there. Now in example K, this actually is pretty similar to what we saw up above in example G, where we have the same inputs here with two trig functions that happen to be a basic antiderivative. And if you remember back to the top of our trig functions, this was the 5th basic antiderivative that we had with the cosecant times the cotangent. So in this case, our u is going to be equal to pi times x, and our du will be pi dx then. Remember, pi is that constant, so we end up with just that constant since x is linear. Now in example L here, we have the integral of 3 times cosine of x times sine of x dx. Here we really want to look at what is our innermost function, and in this case it's this sine of x that I'm underlining, so that u is going to be equal to sine of x. Our du then will be the cosine that's outside the function over here, and so when we end up replacing this, I'm still going to have a sine. I'm still going to have that sine that's outside, and we'll end up with that sine of u then as our integral, or as our integrand then, which is a basic integral to integrate. And in our last example down here, we have -4x times cosine of x squared dx. Since we only have one trig function, my u can't involve that trig function, because if I were to make my u cosine here, I would need a sine in the derivative, which I don't have. So our u this time is actually just going to be that x squared. So our du is going to be 2x dx. Why don't you guys try these 4 examples on your own, as well as the examples G, H, I, and J from when we talked about algebraic functions. And then we'll start our next class by checking all 8 of those as a warm-up.